Good morning. So, last class we have studied about Carnot cycle. Today we are going to discuss about Otto cycle. Before going to the Otto cycle, let us know about the engine on which this Otto cycle is working. That means Otto engine works or the spark ignition engine or petrol engine works on the principle of Otto cycle. So, let us see how the Otto engine works with this video. So, there is a problem with this video. Let me go through the engine. Now, the difference between air standard cycle and IC engine cycle. Here, the process of internal combustion engine is not reversible. All the processes are not reversible, whereas air standard cycle process are reversible. So, that is the major difference between air standard cycle and IC engine cycle. That means processes are not reversible in the case of IC engine, whereas air standard cycle engine process are reversible. Then in the internal combustion engine, air fuel mixture acts as the working fluid. Mixture of air and fuel acts as the working fluid, whereas in the air standard cycle only air is considered to be the working fluid, that with the assumption of ideal gas. That means the air is taken as an ideal gas, assumed as ideal gas. That means it follows the gas laws. That is another difference between these two. And one more is, in the internal combustion engine, the individual processes can't be distinctly identifiable. They overlap, always overlap. In air standard cycle, the processes are distinctly identifiable without any overlap. So, this is another. Each process can't be distinctly identifiable in the case of IC engine, and each process will always overlap. One process will overlap with the another, whereas in the case of air standard cycle, all the processes are distinctly identifiable and they are not overlapping each other. This is another difference between these two. Then in the IC engine, the working fluid specific heat changes with the pressure and temperature. That means specific heat at constant pressure and specific heat at constant volume. These will change with the pressure and temperature, whereas in the air standard cycle it is assumed that air specific heat remains constant. This is the another difference. So, these four differences you should know before going the Otto cycle. Now, Otto cycle is the air standard cycle for the spark ignition engine. SI engine means spark ignition engine. So, this all the petrol engine, that is spark ignition engine, works on the principle of Otto cycle. This cycle contains two reversible adiabatic, that is constant entropy, and two reversible isochoric process, that is constant volume process. That means four processes will constitute the cycle. So, the two processes are reversible adiabatic process, that is constant entropy, and two processes are reversible isochoric process, that is constant volume process in the case of Otto cycle. Now you can see that this PV diagram 1 2 is the air is sucked into the cylinder, 2 3 is the compression, that is adiabatic compression, 3 4 is the constant volume heat addition process, that means here the combustion takes place, 4 5 is the adiabatic expansion where work is done by the gas on the piston, and 5 2 is the exhaust, that means all the combustible gas will be exhausted, and finally all the remaining gases after combustion will be discharged to the atmosphere during 2 1. So, this is the PV diagram process. As I told, there are 2 constant volume process, that is isochoric process, and 2 reversible adiabatic process. This you can see in the PV diagram. Now, you can see this PV diagram again here. 1 2 is the isentropic process, that is reversible adiabatic, and 2 3 is the constant volume heat addition. You can see Q in, heat is added into the system by burning the fuel, and 3 4 is the isentropic expansion, that is reversible adiabatic process. 4 1 is the heat rejection process, that means heat is given out in the case of 4 1. So, this will constitute the Otto cycle. It consists of 4 processes. So, here V 2 is equal to V 3 because it is constant volume process, and V 1 is equal to V 4. This is also a constant volume process. So, that you have to keep it in mind. That you can see this is the isentropic compression process. 1 2 is the isentropic compression, that is reversible adiabatic process. Piston is moving from TDC to BDC, that is 1 to 2, BDC to TDC, that means it is compressed, air is compressed during this stroke adiabatically. Then the 2 3 is the constant volume heat addition process. So, this Otto cycle is also called as constant volume process because heat is added at constant volume. So, you can see here heat is added with the help of a spark produced by the spark plug when the piston is at the top dead center. So, after compressing, the heat is added by burning the fuel with the help of a spark produced by the spark plug. So, this happens with the constant volume, whereas pressure increases. You can see from 2 to 3 pressure increases, P2 to P3. Volume remains constant during this process, constant volume process. Then the next process is the isentropic expansion. So, after the fuel is burnt, it will apply pressure on the piston. Piston moves down from TDC to BDC. Work is done on the piston. So, therefore, this is known as the expansion process, or it is also called as power stroke. Power is produced during this process. So, therefore, it is an isentropic expansion process. 3 4 is isentropic expansion. You can see pressure reduces, volume increases in this process. Then the next process 4 1 is the constant volume heat rejection. Here the heat is given out to the surrounding and the volume remains constant, that is there is no change in volume. Pressure decreases from P4 to P1. Thus, one cycle is completed. This is the Otto cycle process. So, another way of showing the Otto cycle PV diagram and entropy temperature diagram. You can see two constant volume process and two adiabatic process, reversible adiabatic process. So, one is adiabatic compression where the entropy remains constant, that is change in entropy is 0. So, during adiabatic expansion also change in entropy is 0, that means the entropy remains constant. Bc is the heat addition, dA is the heat rejection. Similarly, in the case same thing, you can say the temperature entropy diagram. AB is the adiabatic compression, entropy remains constant. Also the CD is adiabatic expansion, there also the entropy remains constant, whereas BC is the constant volume process and DA also is a constant volume process. So, this is how it represents the Otto cycle in PV diagram and TS diagram, that is temperature entropy diagram. Now, process 1-2 is the intake process. You can say 1-2 is the intake process. The inlet valve open, the piston moves to the right admitting fuel air mixture into the cylinder at constant pressure. So, this is the intake, the air is taken into the cylinder, mixture of fuel air is taken into the cylinder during this process. So, that is in the case of spark ignition engine. Otto cycle is the spark ignition works on Otto cycle. So, therefore, here 1-2 is the air fuel mixture admitting into the cylinder by the movement of the piston. Then the 2-3 is both the valves are closed, the piston compresses the combustible mixture to the minimum value, that you can see here. The 2-3 is constant volume process. So, here compression takes place, and process 3-4 combustion takes place, the mixture is then ignited by means of a spark, combustion takes place and there is an increase in temperature and pressure. Here the combustion takes place, so the spark is produced, combustion takes place and there is no change in volume, whereas temperature and pressure increases here. Then the expansion process, the product of combustion do work on the piston which moves to the right and the pressure and temperature of the gas decreases. Here the work is produced or power is produced during this stroke. So, therefore, expansion, it is expansion, both pressure and temperature decreases in this case. And the exhaust valve opens, next process 5-6, the blow down process, that is exhaust valve open and the pressure drops to the initial pressure, that you can see in the PV diagram, constant volume heat rejection. So, finally it come back to its original position with the exhaust valve open, the piston moves inwards to expel the combustion products from the cylinder at constant pressure. This is how an IC engine works on the Otto cycle, that is spark ignition engine. That you can see here, fuel air mixture is taken by the movement of the valve when the piston moves to the right side. So, that is the intake, then piston moves to the left, that is it is compressed, spark is produced at the end of the compression stroke, it is ignited. So, both the valves are closed in this case and due to the burning of the fuel, it apply pressure on the piston. So, the air is or the power is produced and again the exhaust valve opens. So, all the combustible gas is exhausted into the atmosphere. This is how the IC engine works on Otto cycle. So, these are the PV diagram for the Otto cycle. 1-2 is the compression, that is work is supplying or the work is supplied here. 2-3 is heat addition, Q1 is the heat added, 3-4 is the work produced or power is produced, that is adiabatic expansion, 4-1 heat rejection, Q2. So, the TS diagram is also shown here. 1-2 is constant entropy, that is adiabatic, 2-3 is constant volume, and 3-4 is again constant entropy adiabatic process. 4-1 is the constant volume process. Q1 is the heat supplied, Q2 is the heat rejected. So, air is compressed in process 1-2 reversibly and adiabatically. So, that is 1-2 is compression. Heat is added into air at reversible constant volume process 2-3. 2-3, that is Q1 is the heat added or heat supplied into the system. Work is done by air reversibly and adiabatically in process 3-4. So, process 3-4 is work is done, it is reversible adiabatic process, and heat is rejected at reversible constant volume process 4-1, and the system comes back to its initial state. So, this is how the Otto cycle works here. Now, if M is the mixed mass of air undergoing the cycle of operation, then heat supplied Q1 is equal to Q23. That means at 2-3 process 2-3 heat is supplied at constant volume. So, at constant volume means heat supplied is mCV dt, that is mCV T3 minus T2, that is the heat supplied Q1. Similarly, heat rejected Q2 is Q41, that means during process 41 heat is rejected at constant volume, therefore mCV T4 minus T1. So, these are the two, because Q1 and Q2 is required in order to find the efficiency of the air standard cycle, because the efficiency is the ratio of work done divided by heat supplied. Work done is heat supplied minus heat rejected. So, therefore, this heat supplied and heat rejected should be known. So, that is Q1 is mCV T3 minus T2 and heat rejected Q2 is equal to mCV T4 minus T1. Now, efficiency is given by this, as I told, efficiency is work done divided by heat supplied, but work done is heat supplied minus heat rejected divided by heat supplied. So, this is the efficiency of the Otto cycle. Now, what is the heat supplied and heat rejected is mCV T4 minus T1 is the heat supplied, and heat rejected is mCV T4 minus T1. So, efficiency is 1 minus Q2 by Q1, because Q1 minus Q2 by Q1 you can write this as 1 minus Q2 by Q1, it is 1 minus Q2 is heat rejected mCV T4 minus T1, heat supplied is mCV T3 minus T2. So, that is the efficiency of the Otto cycle. Now, because mCV is constant in the numerator and denominator, you can remove. So, you will left with 1 minus T4 minus T1 divided by T3 minus T2. This is the efficiency of the Otto cycle. Or you can remove the T1 from the numerator as common factor, that you will left with T4 by T1 minus 1, and similarly at the bottom, that is numerator, T2 you can remove, you will left with T3 by T2 minus T1. So, this is by taking out T1 and T2 from the numerator and denominator, you can write the above equation as this 1 minus T1 into T4 by T1 minus 1 divided by T2 into T3 by T2 minus 1. This is the efficiency. Next, the from process 1-2, process 1-2 is adiabatic compression. So, you can say for the adiabatic process, this is the relation between the temperature and pressure. T2 by T1 is V1 by V2 to the power of gamma minus 1. So, this is the ratio between the temperature and volume. From process 3-4 is the adiabatic process, that is adiabatic expansion. Again the relation between these two is temperature and volume. T3 by T4 is equal to V4 by V3 to the power of gamma minus 1. This is from the fundamental that you have studied when you are doing the process, adiabatic process. You have studied the relationship between the temperature and volume. So, but V4 is equal to V1, you can see that is constant volume process. 4-1 is constant volume process. So, therefore, V4 is equal to V1 and V3 is equal to V2. 3-2 is a constant volume process, therefore, V3 is equal to V2. So, you can write V4 by V3 as V1 by V2 to the power of gamma minus 1. So, from the above equation, you can say T2 by T1 is equal to RC or T3 by T4, because both are same. Left hand side, if you take the above two equations, T2 by T1 is V1 by V2 to the power of gamma minus 1. T3 by T4 is equal to V1 by V2 to the power of gamma minus 1. That means left hand sides are equal, therefore, the right hand sides are also equal. Therefore, T2 by T1 is equal to T3 by T4. From the above two equations, we can say like this. So, if you take the efficiency equation, efficiency is 1 minus T1 by T2, that is equal to 1 minus V2 by V1 to the power of gamma minus 1. This is the efficiency of the Otto cycle. Or you can write this as efficiency is equal to 1 minus R1 divided by RC to the power of gamma minus 1. This is the efficiency of the Otto cycle, where RC is the compression ratio, that is V1 by V2. Compression ratio is V1 by V2. So, this is the efficiency of the Otto cycle. That means from this equation you can say that it purely depends on the compression ratio. Efficiency of the Otto cycle depends on the compression ratio only. That means as the compression ratio is increased, the efficiency increases. You can see, because the denominator is high, means that whole term becomes less. So, the 1 minus that is more. So, as the compression ratio increases, efficiency also increases. So, thus you can say the efficiency of the air standards Otto cycle is a function of compression ratio only. The higher the compression ratio, higher the efficiency. But you cannot increase because as the compression ratio is increased, efficiency increases, but it cannot be increased because beyond a certain limit because of noisy and destructive combustion phenomena known as detonation. So, therefore, it can be increased to a certain limit. Beyond that limit, it will become noisy and detonation will occur. So, that can be seen from this graph here, efficiency versus compression ratio. You can see as the compression ratio increases, efficiency also increases. So, this is about the Otto cycle efficiency. Thermal efficiency of Otto cycle increases with the increase in compression ratio, but it cannot be increased beyond certain limit because of the noisy and the combustion phenomena, the destructive combustion phenomena, detonation will occur. So, you can see efficiency gradually becomes flat, it will not increase further. If compression ratio increases after some certain limit, it will remain constant. So, therefore, optimum value you have to find the compression ratio. Now, next is the diesel cycle. So, Otto cycle is used in the spark ignition engine, that means all petrol engine works on the principle of Otto cycle, to constant volume process and to reversible adiabatic process in the case of Otto cycle. Now coming to the diesel cycle, the air standard diesel cycle is an ideal cycle that assumes heat addition occurs during a constant pressure process that starts with the piston at top dead center. So this is the diesel cycle. Here heat is added at constant pressure process, whereas in the case of Otto cycle, heat is added at constant volume process. Therefore, Otto cycle is also known as the constant volume cycle, whereas diesel cycle, heat is added at constant pressure process, so it is called as constant pressure cycle. Now the 4-stroke engine, how it works means, here the intake piston moves from top dead center to bottom dead center, the intake valve or the inlet valve opens, air is drawn into the cylinder. Here this is the difference between the diesel engine and the petrol engine. In the case of petrol engine, that is spark ignition engine, which works on Otto cycle, mixture of air and fuel is taken into the cylinder during the intake, whereas here only air is taken into the cylinder during intake in the case of diesel engine. Now after the intake, the piston moves from BDC to TDC, the air is compressed, it is the compression stroke. Then here after the compression, at the end of the compression, fuel is injected into the cylinder by an injector. So you can see that is another difference here. In the case of petrol engine, spark plug is used to produce the spark to burn the fuel. Here the fuel is injected at the end of the compression stroke by an injector. So because of the very high temperature of the compressed air, the diesel will be ignited here. So ignition of the fuel is due to the temperature produced by the compressed air. Therefore it is called as compression ignition engine, whereas in the petrol engine is a spark ignition engine, because spark is produced to burn the fuel. So fuel is ignited and it does work on the piston, so piston moves downwards, so that is the power stroke. Finally all the gas, combustible gas, has been exhausted into the atmosphere by the movement of the piston from BDC to TDC. This is how the compression ignition engine works, or the diesel engine, which works on the principle of diesel cycle. So therefore you should know how an compression ignition engine works, because diesel engine works on diesel cycle. So you should know the different process involved in this cycle. Now it has got four internally reversible process. 1, 2 is isentropic compression, as in the case of Otto cycle. 2, 3 is the constant pressure heat addition, because in the case of Otto cycle it is constant volume heat addition, here constant pressure heat addition, that means heat is added at constant pressure. And 3, 4 is the isentropic expansion, that is power stroke, and 4, 1 is the heat rejection process. So that is, it will come back to its original state or initial state. Thus one cycle is completed with the help of these 4 processes. So you can see 2 adiabatic process, reversible adiabatic process, 1 constant pressure process and 1 constant volume process. Heat rejection is at a constant volume, whereas heat addition is at a constant pressure. So, this is the diesel cycle. So, this is the compression process. Air is compressed here when the piston moves from BDC to TDC. Then at the end of the compression, heat is added, that means the fuel is injected, fuel is burnt because of the very high temperature of the compressed air. So, heat is added at a constant pressure, and the expansion takes place when the fuel is burnt here. The expansion takes place, piston moves from TDC to BDC. So, that is the expansion process, and the heat rejection process at constant volume, that means piston moves from BDC to TDC. This is how the 4 process in a diesel cycle, that means the diesel engine works on diesel cycle. Now, you can see this air standard diesel cycle here. 1-2 is the adiabatic compression, that is constant entropy. Entropy is constant. 2-3 is the constant pressure process. Heat is added at a constant pressure. 3-4 is expansion, adiabatic expansion, that is isentropic process, that means it is a reversible adiabatic process. So, the entropy remains constant here, that you can see in the TS diagram, temperature entropy diagram. 4-1 is the constant volume heat rejection process. So, Q1 is the heat added, that is during the process 2-3. Q2 is the heat rejected during the process 4-1. Thus, one cycle is completed and the system will come back to its original state 1. So, this 1, 2, 3, 4 and 1 constitute a cycle, that is diesel cycle, and you can see that temperature entropy diagram also. 1, 2 is constant entropy, you can see the vertical line, it is the adiabatic or the reversible adiabatic or isentropic process. 2, 3 is the constant pressure process. So, the temperature increases here from T2 to T3. Then 3, 4 is the expansion process, that is reversible adiabatic. So, entropy remains constant, temperature decreases, also the pressure decreases, volume increases in this process. 4-1 is the heat rejection process, constant volume, volume remains constant, whereas pressure decreases, temperature also decreases, and it come back to its initial state 1. So, this is the air standard diesel cycle PV and TS diagram. Now, the internal view of an diesel engine, because diesel engine works on the diesel cycle. So, the intake is the air is taken into the cylinder, piston moves down. So, that you can see here in the first figure. Then the compression and ignition, when the piston moves from BDC to TDC, air is compressed, the fuel is injected through an injector. So, because of that very high temperature of the compressed air, the diesel is ignited. Then the expansion stroke, that is the third one is expansion. So, piston moves down and power is transferred into the crankshaft to the connecting rod and the crank. Finally, all the combustible gas is exhausted into the atmosphere when the piston moves from BDC to TDC. So, this is how the diesel engine works. This is the internal view of a diesel engine. 4 process: intake, compression and injection, then the expansion, and finally the exhaust. This is also you can see in a line diagram. It is the valve, air is admitted, there will be a fuel valve because fuel is injected here at the end of the compression stroke. So, therefore, fuel injector or fuel valve is required, and there is an exhaust valve. So, 1, 2 is intake, 2, 3 is compression, 3, 4 is heat addition, 4, 1 is expansion, and 4 5 is expansion, 5 1 is the heat rejection, and back to 1 5 1 is the exhaust. So, this is the PV diagram of the diesel engine. Now, diesel cycle is the A standard cycle for the compression ignition engine. So, the Otto cycle is the A standard cycle for spark ignition engine, whereas diesel cycle is the A standard cycle for compression ignition engine. Now, limitation of compression ratio of spark ignition can be overcome by compressing air alone. So, in the case of the spark ignition engine, the compression ratio, the efficiency of the compression ratio, the efficiency of the Otto cycle depends on the compression ratio. So, you cannot increase beyond certain limit in the case of Otto cycle, that what we have discussed. So, that limitation can be overcome by compressing air alone instead of fuel air mixture, because when you compress the air fuel mixture beyond certain limit, then there will be a destructive combustion takes place, that is detonation takes place. Therefore, you cannot increase or compress the air fuel mixture beyond certain limit. So, here that can be avoided by compressing the air alone instead of mixture of air and fuel, then injecting the fuel into the cylinder when the combustion is required. So, it can be injected, fuel is injected at the end of the compression stroke. After compressing the air and the fuel is injected, because of the high temperature of the compressed air, the diesel is ignited here. Whereas in the case of a spark ignition engine, the spark plug is used to produce the spark in order to burn the fuel or ignite the fuel. So, temperature of the air after compression must be high enough so that fuel sprayed into the hot air burns the fuel spontaneously. So, that is the principle adopted here. It has to be compressed, air has to be compressed, and temperature should be very high, so that as soon as the diesel is injected or fuel is injected at the end of the compression stroke, it is ignited spontaneously. Now, process 1 2 is intake, that is the air valve opens, the piston moves out, admitting air into the cylinder at constant pressure. Then 2 3 is the compression. The air which has been taken into the cylinder during the intake is compressed when the piston moves from BDC to TDC at the volume if both the valves are closed. Then process 3 4 is the fuel injection and combustion. So, at the end of the compression stroke, the fuel is injected through an injector or it is sprayed over the hot air and combustion takes place. So, that is process 3 4. It takes place at constant pressure. Then 4 5 is the expansion. The combustion of the products expand doing work on the piston, which moves out to the maximum volume. So, that is the expansion stroke. So, fuel injection and combustion is process 3 4. Process 4 5 is the expansion. Then the blow down, that means exhaust valve is open and the pressure dropped to the initial pressure of the combustible mixture drops to the initial pressure, because exhaust valve opens and all the gases will be exhausted. And 6 1, process 6 1 is exhaust, that is all the combustible gas is exhausted into the atmosphere through the exhaust valve when the piston moves from BDC to TDC. So, one cycle is completed, that you can see here PV diagram and TS diagram for the diesel cycle. So, 1 2 is the adiabatic compression. 2-3 is the constant pressure heat addition. You can see Q1 is the heat addition. 3-4 is the expansion, that means power is produced during this stroke or this process. 4-1 is the heat rejection process, Q2 at constant volume. So that you can see in the PV diagram, same as TS diagram, 1-2, 2-3, 3-4 and 4-1. 1-2 is the constant entropy, that is reversible adiabatic process. 2-3 is the constant pressure process. You can see here during the Otto cycle, the 2-3 process where the volume is constant, that is drawn at the top of the 2-3 process here, that is pressure, constant pressure process in the case of diesel cycle, and Otto cycle 2-3 is the constant volume process. So that is shown V is equal to C in the TS diagram, temperature entropy diagram. That means temperature is high in the case of the Otto cycle. Now 3-4 is the expansion process, that means power is produced, adiabatic expansion. 4-1 is the constant volume process, heat is rejected, Q2 is the heat rejected here. Now air is compressed in the process 1-2 reversibly and adiabatically, that is 1-2. Heat is added into air at a reversible constant pressure process, that is 2-3. Work is done by air reversibly and adiabatically in process 3-4, and heat is rejected reversibly at a constant volume, that is process 4-1, and the cycle is repeated again, one more cycle will be there. Now the m is the mass of the air undergoing the cycle of operation. Then heat supplied Q1 is during 2-3 process mCp T3 minus T2, because it is a constant pressure process, heat is added at constant pressure, therefore it is mCp, where Cp is the specific heat at constant pressure. Similarly, heat rejected Q2 is equal to Q41, that is during 4-1 process the heat is rejected, that is at constant volume, therefore mCv T4 minus T1. So Cv means the specific heat at constant volume, because heat is rejected at constant volume, it is mCv T4 minus T1, and heat is supplied is Q1, that is mCp T3 minus T2, because it is constant pressure process. Now the efficiency is work done divided by heat supplied. So that is the efficiency of any air standard cycle, work done by heat supply. That work done is the output, heat supplied is the input. So therefore work done is the difference in heat supplied and heat rejected, that gives the work done, that is heat supplied minus heat rejected by heat supplied. Heat supplied is Q1, heat rejected is Q2. So if you substitute here, you will get efficiency as 1 minus Q2 by Q1, that is 1 minus mCv T4 minus T1 divided by mCp T3 minus T2. So this is Q2 is at constant volume, heat rejection, and Q1 is the heat supplied at constant pressure. So that is mCp T3 minus, or you can write this equation as 1 minus is same in the numerator and denominator, that you can cancel. Cv and Cp is there, divide both numerator and denominator by Cv, you will get T4 minus T1 divided by gamma, gamma is Cp by Cv, that is ratio of specific heat, that is gamma into T3 minus T2. So, this is the efficiency of the diesel cycle. Further, it is the to simplify, the temperature, all the temperature has to be expressed either in terms of compression ratio or expansion ratio. That I will continue in the next class. Thank you.